Time feels like something we understand. It moves forward, second by second, carrying everything with it. Space feels even more certain. It surrounds us in every direction, stretching outward into what we imagine as an endless universe. We walk through space, we measure time, and together they form the stage where all of existence unfolds. But what if this understanding is incomplete? What if time and space are not what they seem? What if they are not separate, not fixed, and not even fundamental in the way we believe? For most of human history, time and space were seen as absolute. Time ticked forward at a constant rate everywhere, unaffected by anything. Space was a rigid, unchanging grid, a backdrop where matter existed and events occurred. This idea felt natural because it matched everyday experience. A clock in one place seemed to tick at the same rate as a clock somewhere else. A meter in length did not change simply because it was moved. Reality appeared stable and predictable. But this comforting view began to crack as science advanced. Observations of the universe revealed inconsistencies that could not be explained by classical ideas. Light, the fastest thing known, behaved in ways that challenged intuition. Experiments showed that no matter how fast you moved, the speed of light remained constant. This single fact would unravel centuries of understanding and force a complete rethinking of time and space. Imagine two observers moving relative to each other. According to everyday logic, they should measure different speeds for a beam of light. If one observer is chasing the light, it should appear slower. If another is moving toward it, it should appear faster. Yet experiments showed this never happens. Light speed remains the same for all observers, regardless of their motion. This is not just a strange detail. It is a fundamental clue about the nature of reality. To make sense of this, something deeper had to change. It turned out that time itself adjusts. Space itself adjusts. They are not fixed. Instead, they are flexible and interconnected. When motion changes, time can slow down or speed up. Distances can shrink or expand. What one observer measures as a second or a meter can differ for another. Reality becomes relative, shaped by motion and perspective. This idea is difficult to accept because it contradicts our daily experience. At human speeds, these effects are too small to notice. But as speeds approach that of light, the changes become dramatic. A clock moving at high speed will tick more slowly compared to a stationary one. This is not an illusion. It is a measurable, physical effect. Time itself is stretched. The same applies to space. Objects in motion contract along the direction of travel. Again, this is not a trick of perception. It is a real transformation. Space and time are not separate entities, but parts of a unified structure known as space-time. This concept reshapes everything. Instead of imagining space as a stage and time as a clock ticking independently, we must see them as woven together into a single fabric. This fabric is not static. It can bend, twist, and change. Massive objects like planets and stars influence it. They do not simply sit within space. They reshape it. Gravity once thought of as a force pulling objects together, is actually the result of this curvature. Objects follow the paths defined by the bending of space-time. They are not pulled in the traditional sense. They are guided by the geometry of the universe itself. Consider standing on the surface of Earth. You feel gravity pulling you downward, but from a deeper perspective, you are following the natural path through curved space-time. Earth's mass bends the fabric around it, and your motion follows that curvature. If you were to remove Earth, the curvature would disappear, and so would the effect we call gravity. This shift in understanding transforms how we view motion and rest. There is no absolute frame of reference, no universal clock ticking the same for everyone. Each observer carries their own measurement of time and space, shaped by their motion and surroundings. Reality becomes a network of perspectives, all valid within their own frame. Even more surprising is the idea that time is not as straightforward as it seems. We experience it as a steady flow from past to present to future. But this flow may not be a fundamental feature of the universe. Instead, it could be a result of how we perceive events. In the deeper structure of space-time, all moments may coexist. Past, present, and future could be part of a single unified whole. Imagine a timeline not as something that moves, but as something that exists all at once. Every event that has happened or will happen is laid out within the fabric of space-time. Our consciousness moves along this structure, giving the illusion of time passing. This idea challenges everything we take for granted. It suggests that the future may already exist in some sense, just as the past does. But if time is not truly flowing, why do we perceive it that way? The answer may lie in entropy, a concept from thermodynamics. Entropy measures the level of disorder in a system. The second law of thermodynamics states that entropy tends to increase over time. This gives direction to time, creating what we call the arrow of time. We remember the past because it was more ordered. We move toward the future because it is more disordered. This arrow of time gives structure to our experience. It separates cause from effect. It allows us to build memories and anticipate outcomes. Without it, time would feel directionless. Events would not have a clear sequence. Our understanding of reality would collapse into confusion. Yet even this arrow is not fundamental in the same way as space-time. It emerges from the behavior of systems, not from the underlying laws themselves. At the deepest level, the laws of physics do not distinguish between past and future. They work the same in both directions. This symmetry suggests that the flow of time is not built into the fabric of the universe, but arises from the way complex systems evolve. As we explore further, the illusion of simplicity continues to break down. Space itself is not empty. It is filled with energy and activity at the smallest scales. Quantum mechanics reveals a world where particles appear and disappear, where uncertainty replaces certainty, and where reality becomes probabilistic. Space is not a passive stage, but an active participant in the dynamics of the universe. At these tiny scales, the concept of distance becomes blurred. Particles can be entangled, meaning their properties are linked regardless of the space between them. Changes to one can instantly affect the other, even across vast distances. This phenomenon challenges our understanding of locality, the idea that objects are only influenced by their immediate surroundings. Time also behaves strangely in the quantum realm. Processes do not always have a clear sequence. Events can occur in ways that defy classical logic. The deeper we look, the less familiar reality becomes. The solid, predictable world we experience emerges from a much more complex and mysterious foundation. All of this points to a profound conclusion. Time and space are not the ultimate building blocks of the universe. They are part of a larger framework, one that we are only beginning to understand. Our everyday experience is shaped by these concepts, but they do not define the full nature of reality. The journey to uncover this deeper truth has only just begun. Scientists are working to unify the theories of relativity and quantum mechanics into a single framework known as quantum gravity. This theory aims to describe how space-time behaves at the smallest scales, where the effects of both gravity and quantum mechanics are significant. Early ideas suggest that space-time may not be continuous. Instead, it could be made up of tiny, discrete units, like pixels in an image. At this scale, the smooth fabric we imagine breaks down into a more fundamental structure. Time itself may also be quantized, existing in smallest possible intervals. Other theories propose that space-time emerges from something even more basic. It may arise from networks of information or relationships between quantum states. In this view, space and time are not fundamental ingredients, but emergent properties like temperature or pressure. They arise from deeper processes that do not resemble anything we experience directly. If this is true, then our understanding of reality must change completely. The universe is not built from space and time. Instead, space and time are tools our minds use to interpret a deeper, more abstract reality. They are part of the interface between human perception and the true nature of existence. This realization is both unsettling and exciting. It means that what we see and feel is not the full picture. There are layers of reality beyond our senses, waiting to be discovered. It also means that the universe is far more complex and fascinating than we ever imagined. As we stand at the edge of this understanding, we begin to see that the familiar world is just a surface. Beneath it lies a deeper structure, one that challenges our intuition and expands our sense of what is possible. Time and space, once thought to be the foundation of everything, are revealed as part of a larger story. And this is only the beginning. Before there was time as we know it, before there was space stretching across unimaginable distances, there was something far stranger. The universe did not begin as an explosion in space. It was the beginning of space itself. This idea is difficult to grasp because it challenges the way we imagine events. Every explosion we know happens somewhere inside space and unfolds over time. But the birth of the universe was not like that. There was no outside, no empty void waiting to be filled. There was no ticking clock counting down to the moment. Space and time came into existence together, emerging from a state that defies ordinary understanding. To understand this, we have to abandon familiar images. The universe did not expand into anything. Instead, it expanded as everything. Every point in space moved away from every other point, not because they were traveling through a pre-existing void, but because the fabric of space itself was stretching. Imagine drawing dots on the surface of a balloon and then inflating it. As the balloon grows, the dots move apart, even though none of them is at the center of expansion on the surface. This analogy is imperfect, but it hints at the idea. The universe has no center in space. The expansion happens everywhere at once. In the earliest moments, the universe was incredibly hot and dense. All the energy that would later form galaxies, stars, and planets was compressed into a tiny region. Temperatures were so extreme that the familiar forms of matter could not exist. At this stage, there were no atoms, no particles as we know them, only a seething, energetic state where the distinctions between forces and matter were blurred. As the universe expanded, it cooled. This cooling allowed structure to emerge. Fundamental forces that were once unified began to separate. Gravity, electromagnetism, and the nuclear forces took on their distinct roles. Particles formed, collided, and transformed. The early universe was a dynamic, rapidly changing environment where the seeds of all future structure were being planted. One of the most remarkable features of this process is how quickly it happened. Within fractions of a second, the universe underwent dramatic changes. A period known as cosmic inflation may have occurred, during which the universe expanded at an extraordinary rate. In an instant, it grew from something unimaginably small to something vastly larger. This rapid expansion smoothed out irregularities and set the stage for the large-scale structure we observe today. Inflation also helps explain why the universe appears so uniform. When we look in different directions, we see regions of space that are incredibly similar, even though they are separated by enormous distances. Without inflation, these regions would never have been in contact. They would not have had time to exchange information or energy, yet they share the same temperature and properties. Inflation provides a mechanism for this uniformity, stretching a once small, connected region across the entire observable universe. After inflation, the expansion continued, but at a slower pace. The universe was still hot, filled with a dense plasma of particles and radiation. Photons, the particles of light, could not travel freely because they constantly interacted with charged particles. The universe was opaque, more like a glowing fog than the clear expanse we see today. As time passed, the universe cooled further. Eventually, it reached a point where electrons and protons could combine to form neutral atoms. This process, known as recombination, marked a major transition. With fewer charged particles to scatter them, photons were able to travel freely for the first time. The universe became transparent. The light released at this moment still fills the cosmos today as a faint glow known as the cosmic microwave background. This ancient light carries a snapshot of the universe at that early stage. It reveals tiny variations in temperature and density, subtle differences that would later grow into galaxies and clusters. These fluctuations were the seeds of structure, amplified over billions of years by gravity. Regions that were slightly denser attracted more matter, growing larger and more complex. The formation of the first stars marked another turning point. These stars ignited from clouds of gas collapsing under their own gravity. Inside them, nuclear fusion began, producing light and heavier elements. The first stars were different from those we see today. They were larger, hotter, and shorter lived. When they ended their lives in powerful explosions, they scattered elements into space, enriching the cosmic environment. From this process, new generations of stars formed, along with planets and eventually the conditions necessary for life. Everything we see today, from the smallest grain of dust to the largest galaxy, traces its origin back to those early moments. The atoms in our bodies were forged in the hearts of stars, themselves born from the expanding universe that began with the emergence of space and time. Yet even as we trace this history, fundamental questions remain. What caused the universe to begin? What existed before the Big Bang, if the concept of before even makes sense? These questions push the limits of our understanding. In many theories, time itself begins at the Big Bang. If time did not exist before this moment, then asking what came before may not be meaningful in the usual sense. Some models suggest that the universe could have emerged from a quantum fluctuation, a spontaneous event in a deeper underlying reality. In quantum physics, particles can appear and disappear seemingly from nothing. If this behavior extends to the fabric of the universe itself, it might explain how something can arise without a traditional cause. However, this idea is still speculative and raises as many questions as it answers. Other theories propose that our universe is just one of many, part of a larger multiverse. In this view, the Big Bang is not a unique beginning, but one of countless events happening across a vast, possibly infinite landscape. Each universe could have its own properties, its own laws of physics, and its own version of space and time. There are also models where the universe undergoes cycles of expansion and contraction. In these scenarios, the Big Bang is not the absolute beginning, but a transition from a previous state. The universe could collapse and then rebound, starting a new phase. These ideas challenge the notion of a singular origin and suggest a more complex cosmic history. Despite these uncertainties, the evidence for the expansion of the universe is strong. Observations of distant galaxies show that they are moving away from us, with more distant ones receding faster. This pattern is consistent with an expanding space. The cosmic microwave background provides further confirmation, offering a detailed map of the early universe that matches predictions from theoretical models. The success of these models gives us confidence in our understanding, but it also highlights the limits of current knowledge. As we probe earlier and earlier times, conditions become more extreme and our theories become less certain. The combination of quantum mechanics and gravity remains incomplete, leaving a gap in our understanding of the very beginning. What is clear is that space and time are not static backdrops. They are dynamic, evolving entities that have a history. They were born, they changed, and they continue to evolve. The universe is not a fixed stage, but a process unfolding over billions of years. This realization transforms our perspective. We are not separate from the universe. We are part of its story, shaped by the same processes that created galaxies and stars. The passage of time we experience is tied to the evolution of the cosmos. The space we move through is part of a structure that began with the birth of the universe itself. As we continue to explore, we find that the deeper we look, the more interconnected everything becomes. The origin of space and time is not just a distant event. It is the foundation of our existence, influencing every moment, every interaction, every piece of matter. The story of the universe is not just about what happened long ago. It is about the nature of reality itself. It is about how something as fundamental as time and space can emerge, evolve, and shape everything we know. And even now, the expansion continues. Galaxies drift farther apart. The cosmic web stretches and changes. The universe is still becoming, still unfolding, still revealing its secrets. Space feels empty. When we look up at the night sky, the vast darkness between stars and galaxies gives the impression of nothingness, a silent void where matter is scattered like distant islands. For a long time, this emptiness was taken literally. Space was thought to be a passive container, a stage where the drama of the universe played out without influencing the actors within it. But this idea, like many others, would eventually collapse under closer examination. Space is not nothing. It has structure, behavior, and even energy. It can stretch, curve, ripple, and interact with everything it contains. To begin understanding this, we must shift our thinking from space as a backdrop to space as an active participant. The concept of space-time brings this idea into focus. Instead of imagining space and time as separate, we see them as interwoven into a single four-dimensional fabric. This fabric is not rigid. It is dynamic and responsive. It reacts to the presence of energy and mass, changing its shape in ways that affect the motion of objects. Imagine placing a heavy object on a stretched sheet. The sheet bends under the weight, creating a depression. If a small object moves nearby, it will follow a curved path, not because there is a force pulling it directly, but because the surface it moves across is no longer flat. This analogy, while simplified, captures the essence of how gravity works in the framework of space-time. Massive objects do not simply exert forces across empty space, they reshape the geometry of the universe itself. This curvature is not just a theoretical idea, it has measurable effects. Light, which travels in straight lines through flat space, bends when it passes near massive objects. This phenomenon, known as gravitational lensing, allows us to see distant galaxies whose light has been curved around closer ones. It also provides a powerful tool for studying the distribution of mass in the universe, including forms of matter that do not emit light. Time is also affected by this curvature. Clocks in stronger gravitational fields tick more slowly than those in weaker fields. This effect, known as gravitational time dilation, has been confirmed through experiments on Earth and observations in space. Even the difference in gravity between the surface of Earth and higher altitudes leads to tiny but measurable differences in the passage of time. This means that time is not universal. It depends on where you are and how you are moving. The fabric of space-time is constantly changing. Planets orbit stars, stars orbit galaxies, and galaxies move within larger cosmic structures. These motions are guided by the curvature of space-time, but they also contribute to it. The universe is a complex, interconnected system where matter and geometry influence each other continuously. But the story does not end with curvature. Space-time can also ripple. When massive objects accelerate, especially in violent events like the collision of black holes, they create disturbances that propagate outward at the speed of light. These disturbances are known as gravitational waves. They are like ripples on the surface of a pond, but instead of water, they travel through the fabric of space-time itself. The detection of gravitational waves opened a new window into the universe. For the first time, we could observe cosmic events not through light, but through the vibrations of space-time. These signals carry information about some of the most extreme phenomena in the cosmos, offering insights into regions that would otherwise remain hidden. The existence of gravitational waves confirms that space-time is not static. It can move, stretch, and carry energy. This challenges the idea of emptiness even further. Space is not just something that exists, it is something that behaves. At even smaller scales, the nature of space becomes even more complex. Quantum theory suggests that what we perceive as empty space is actually filled with activity. Virtual particles constantly appear and disappear, flickering into existence for brief moments before vanishing again. These fluctuations are not directly observable in the traditional sense, but their effects can be measured. This quantum activity means that space has a kind of underlying energy, often referred to as vacuum energy. This energy is not associated with any particular object, yet it influences the behavior of the universe on large scales. Some theories suggest that this energy may be related to dark energy, the mysterious force driving the accelerated expansion of the universe. If space contains energy, then it is far from empty. It is a dynamic environment where processes occur even in the absence of matter. This realization changes how we think about the vacuum. It is not a void, but a sea of potential, constantly fluctuating and interacting. The structure of space-time also raises questions about its continuity. Is it truly smooth, or is it made up of discrete units at the smallest scale? Some theories propose that space-time is quantized, composed of tiny, indivisible pieces. At this level, the familiar notion of distance may break down. Points in space may not be infinitely divisible, but instead connected through a network of relationships. In such a framework, the geometry of space-time could emerge from more fundamental elements. Instead of being a continuous fabric, it might resemble a web or a lattice where connections define structure. This idea is still under investigation, but it offers a possible path toward unifying the principles of relativity and quantum mechanics. Another intriguing possibility is that space-time is not fundamental at all. It may emerge from deeper processes, much like temperature emerges from the motion of particles. In this view, space and time are effective descriptions of a more basic reality. They are tools that work at large scales, but may not apply at the smallest levels. This perspective challenges the very foundation of physics. If space-time is emergent, then the true nature of the universe lies beyond it. Understanding this deeper layer could reveal new principles and lead to a more complete theory of everything. As we consider these ideas, it becomes clear that our everyday experience is limited. We perceive space as three-dimensional and time as a separate flow, but this is a simplified picture. The true structure of reality is far more intricate. It involves dimensions, interactions, and behaviors that are not directly accessible to our senses. Despite these challenges, the concept of space-time has proven incredibly powerful. It allows us to describe the motion of planets, the behavior of light, and the evolution of the universe with remarkable accuracy. It provides a framework for understanding phenomena that would otherwise seem impossible. Yet even this framework is incomplete. It works well in many situations, but it breaks down under extreme conditions, such as inside black holes or at the very beginning of the universe. In these regimes, new physics is required, physics that can account for both the curvature of space-time and the uncertainty of the quantum world. The search for this new understanding is one of the greatest challenges in science. It requires not only new theories, but also new ways of thinking. It forces us to question assumptions that have guided us for centuries and to embrace ideas that may seem counterintuitive. As we move forward, we continue to uncover clues. Observations of the cosmos reveal patterns and behaviors that hint at deeper truths. Experiments probe the limits of our theories, testing their predictions and revealing their shortcomings. Each discovery brings us closer to a more complete picture, even as it raises new questions. The fabric of space-time, once thought to be simple and unchanging, is now understood as a dynamic, complex entity. It shapes the universe and is shaped by it. It carries energy, responds to motion, and may even emerge from deeper principles. In this unfolding story, space is no longer empty. It is alive with structure and activity, a fundamental part of the cosmos that holds the key to understanding everything else. For centuries, gravity was understood in a simple and intuitive way. Objects fell toward the ground because an invisible force pulled them. Planets orbited the sun because they were held in place by this same force, acting across the vast emptiness of space. This idea, formalized through classical physics, worked remarkably well. It explained motion on Earth and in the heavens with precision. It allowed predictions of planetary orbits, the motion of comets, and even the tides of the oceans. Gravity was seen as a fundamental interaction, a force acting instantly across distance, binding the universe together. But there was a problem hidden within this success. The concept of an instantaneous force acting across space raised deeper questions. How could something influence another object without any delay, without any medium, without any visible connection? As understanding of light and electromagnetism advanced, scientists began to realize that signals could not travel infinitely fast. There appeared to be a universal speed limit, the speed of light. If this limit applied to all interactions, then gravity could not act instantaneously. Something in the classical picture had to be incomplete. The breakthrough came with a radical shift in thinking. Instead of treating gravity as a force, it could be understood as a property of space and time themselves. This idea required reimagining the universe at its most fundamental level. Space was no longer a passive stage. Time was no longer an independent flow. Together, they formed a dynamic structure that could be shaped by the presence of energy and matter. In this new framework, massive objects do not pull on each other through empty space. Instead, they alter the geometry around them. The presence of mass causes space-time to curve, and objects move along paths determined by this curvature. These paths, known as geodesics, represent the natural motion of objects in a curved space-time. What we perceive as gravitational attraction is actually the result of following these curved paths. This shift in perspective resolves the problem of instantaneous action. Changes in the distribution of mass or energy do not produce immediate effects everywhere. Instead, they propagate through space-time at a finite speed, the speed of light. If a massive object were to suddenly move, the change in curvature would spread outward like a wave, influencing other objects only after a delay. Gravity becomes a local interaction, mediated by the geometry of space-time rather than a mysterious force acting at a distance. One of the simplest ways to visualize this is to imagine a planet orbiting a star. In the classical view, the star pulls on the planet, keeping it in orbit. In the geometric view, the star creates a curved region of space-time around it. The planet moves through this curved region, following the straightest possible path within that curved geometry. Its motion appears as an orbit, not because it is being pulled inward, but because the space it moves through is not flat. This idea extends to all forms of motion. Objects in freefall are not being pulled downward in the traditional sense. They are moving along natural paths in curved space-time. From their own perspective, they feel no force at all. This is why astronauts in orbit experience weightlessness. They are in freefall, moving along geodesics around Earth. Even though gravity is still shaping their motion, they do not feel it as a force. This principle leads to one of the most profound insights about gravity. Locally, the effects of gravity are indistinguishable from the effects of acceleration. If you are inside a closed box, you cannot tell whether the force you feel is due to gravity or to acceleration of the box itself. This equivalence between gravity and acceleration forms the foundation of the geometric understanding of gravity. From this starting point, a complete description of how space-time responds to matter and energy can be developed. The equations that describe this relationship are complex, but their meaning is clear. They state that matter and energy tells space-time how to curve, and space-time tells matter how to move. This interplay creates the dynamic structure of the universe. One of the earliest confirmations of this idea came from observations of light bending around massive objects. According to the geometric model, light should follow curved paths when passing through curved space-time. This effect was observed during a solar eclipse, when starlight passing near the Sun was deflected. The measured deflection matched the predictions of the new theory, providing strong evidence for the curvature of space-time. Another confirmation comes from the behavior of time in gravitational fields. Clocks closer to massive objects run more slowly than those farther away. This effect has been measured with incredible precision, using atomic clocks placed at different altitudes. Even small differences in height lead to measurable changes in the passage of time. This is not just a theoretical prediction, it is a real effect that must be accounted for in modern technologies such as satellite navigation systems. The geometric view of gravity also predicts the existence of extreme objects where the curvature of space-time becomes very strong. Among these are black holes, regions where the curvature is so intense that not even light can escape. The boundary of such a region, known as the event horizon, marks a point of no return. Once an object crosses this boundary, it cannot communicate with the outside universe. Black holes represent the limits of our current understanding. Inside them, the curvature of space-time becomes so extreme that the equations describing it break down. This suggests that our theory is incomplete and that a deeper framework is needed to fully describe these conditions. The influence of curved space-time extends beyond individual objects. It shapes the large-scale structure of the universe. The expansion of the universe, the motion of galaxies, and the formation of cosmic structures are all influenced by the geometry of space-time. Gravity is not just a local phenomenon, it governs the evolution of the cosmos as a whole. The discovery of gravitational waves provided another powerful confirmation of this framework. When massive objects accelerate, they produce ripples in space-time that travel outward. These waves carry energy and information about the events that created them. Their detection opened a new way of observing the universe, allowing us to study phenomena that do not emit light. The existence of gravitational waves also reinforces the idea that space-time is dynamic. It is not a fixed background, but an active entity that can change, move, and interact. This challenges our intuition, but provides a more accurate description of reality. Despite its success, the geometric theory of gravity is not the final answer. It works extremely well at large scales, describing planets, stars, and galaxies. But at very small scales, where quantum effects become important, it faces difficulties. The smooth, continuous picture of space-time does not easily fit with the probabilistic nature of quantum mechanics. This mismatch suggests that a deeper theory is needed, one that can unify the principles of geometry and quantum behavior. Such a theory would provide a more complete understanding of gravity and the structure of the universe. It might reveal that space-time itself is not fundamental, but emerges from more basic elements. As we explore these ideas, it becomes clear that our understanding of gravity has undergone a profound transformation. What was once seen as a simple force is now understood as a manifestation of the geometry of space-time. This shift changes not only how we describe motion, but also how we think about the nature of reality. The universe is not held together by invisible forces acting across empty space. It is shaped by the curvature of a dynamic fabric that responds to the presence of matter and energy. Objects move not because they are pulled, but because they follow the natural paths defined by this curvature. This insight opens the door to new possibilities. It allows us to explore phenomena that were once beyond reach. It challenges us to rethink fundamental concepts and to look deeper into the structure of the cosmos. And as we continue this journey, we begin to see that the true nature of gravity is not just about attraction. It is about the shape of the universe itself, a shape that is constantly evolving, constantly interacting, and constantly revealing new layers of reality. Time seems steady and reliable. It moves forward in a way that feels constant, unaffected by anything around us. Seconds pass at the same pace whether we are resting or moving, whether we are on Earth or looking up at the stars. This assumption feels so natural that it rarely comes into question. But as our understanding deepens, it becomes clear that time is far more flexible than we ever imagined. It does not flow at the same rate everywhere. It is influenced by motion and gravity, stretching and compressing, depending on the conditions of the observer. To understand this, we must let go of the idea of a universal clock. There is no single timeline that governs the entire universe. Instead, each observer experiences their own version of time, shaped by their movement and their position within gravitational fields. This is not just a philosophical idea. It is a measurable and well-tested feature of reality. One of the most striking aspects of this behavior is known as time dilation. When an object moves at high speed, its internal clock slows down relative to a stationary observer. This means that time itself passes more slowly for something in motion. If two identical clocks are synchronized and one is sent on a high-speed journey while the other remains still, the moving clock will show less elapsed time when they are reunited. This is not a flaw in the clocks. It is a fundamental effect of how time works. At everyday speeds, this effect is incredibly small. Even the fastest vehicles we use produce changes in time that are far too tiny to notice. But as speeds approach the speed of light, the effect becomes dramatic. Time slows down significantly, and at the limit of light speed, it would appear to stop entirely from the perspective of an outside observer. This leads to one of the most fascinating consequences of relativity. If a person were able to travel at speeds close to the speed of light, they would experience time differently from those who remain behind. A journey that feels short to the traveler could correspond to many years passing for others. This is often illustrated through thought experiments involving twins, where one travels at high speed and returns younger than the other. While this scenario is simplified, the underlying principle is real and has been confirmed through experiments with fast-moving particles and precise clocks. Motion is not the only factor that influences time. Gravity also plays a crucial role. In regions of stronger gravitational fields, time passes more slowly compared to regions of weaker gravity. This effect, known as gravitational time dilation, arises from the curvature of space-time. The deeper an object is within a gravitational well, the more space-time is curved and the slower time flows relative to distant observers. This effect has been measured with remarkable precision. Atomic clocks placed at different altitudes on Earth show slight differences in their rates. A clock at sea level ticks more slowly than one on a mountain. The difference is tiny, but it is consistent and measurable. In orbit, the effect becomes even more pronounced. Satellites experience weaker gravity than objects on Earth's surface, causing their clocks to run faster. At the same time, their motion causes time to slow down. Both effects must be accounted for to ensure the accuracy of satellite-based systems. These phenomena reveal that time is not an independent, universal quantity. It is intertwined with space and influenced by the same factors that shape the geometry of the universe. Time is part of the fabric of space-time, and its flow depends on how that fabric is stretched and curved. Another surprising consequence of relativity is the relativity of simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another. This depends on their relative motion. If two events occur at different locations, observers moving differently may disagree about the order in which they happen. This challenges the intuitive idea that there is a single, objective, present moment shared by all. The concept of a universal present dissolves under this framework. Instead of a single moment that spans the universe, each observer has their own slice of space-time that defines what they consider to be now. These slices can differ depending on motion, leading to different interpretations of when events occur. This does not create contradictions, but it does require a new way of thinking about time and sequence. This leads to a deeper philosophical question. If there is no universal present, what does it mean for time to pass? Our experience suggests a continuous flow, a movement from past to future. But in the space-time framework, all events exist within a four-dimensional structure. Past, present, and future are not separate realms, but different regions of this structure. In this view, time does not flow in the way we perceive. Instead, our consciousness moves along a path through space-time, experiencing events in sequence. The sense of progression may arise from the way our brains process information, creating a narrative from the events we encounter. This idea is often referred to as the block universe concept, where all moments exist simultaneously within the structure of space-time. While this interpretation is compelling, it raises challenging questions about free will and the nature of reality. If the future already exists in some sense, does that mean it is fixed? Or is the structure of space-time itself dynamic, with multiple possible paths that depend on quantum events and interactions? These questions remain open and are the subject of ongoing research and debate. The connection between time and entropy provides another perspective on the flow of time. Entropy, which measures disorder, tends to increase in closed systems. This increase gives direction to time, creating the arrow of time that distinguishes past from future. We remember the past because it is associated with lower entropy, and we move toward the future where entropy is higher. This arrow of time is deeply connected to our experience. It explains why we cannot remember the future, why causes precede effects, and why processes like mixing and decay are irreversible. However, at the fundamental level, many physical laws do not distinguish between forward and backward directions in time. They work equally well in both directions. This suggests that the arrow of time is not a fundamental property of the laws themselves, but an emergent feature arising from initial conditions and statistical behavior. In extreme environments, the behavior of time becomes even more unusual. Near massive objects, like black holes, gravitational time dilation becomes so strong that time nearly stops relative to distant observers. An object falling toward a black hole appears to slow down as it approaches the event horizon, its clock ticking ever more slowly. From the perspective of the falling object, however, time continues normally, and it crosses the boundary without noticing anything special at that exact point. This difference in perspective highlights the relative nature of time. There is no single absolute description that applies to all observers. Each frame of reference provides its own valid account, and understanding the full picture requires considering all of them together. Time dilation also plays a role in the behavior of particles at high energies. In particle accelerators, particles moving at speeds close to that of light experience time more slowly. This allows unstable particles to exist longer than they would at rest, traveling greater distances before decaying. These observations provide direct evidence of time dilation and confirm the predictions of relativity. As we continue to explore the nature of time, it becomes clear that it is not a simple, uniform flow. It is a dynamic aspect of space-time, influenced by motion, gravity, and the structure of the universe. It can stretch, slow, and vary depending on the conditions of the observer. This understanding challenges our intuition but also enriches our view of reality. It reveals a universe where time is not fixed but flexible, not absolute but relative. It shows that the passage of time we experience is just one perspective within a much larger and more complex framework. The deeper we look, the more we realize that time is not what it seems. It is not just a measure of change or a backdrop for events. It is an active part of the universe, shaped by the same forces that shape space itself. And as we continue this journey, we begin to see that understanding time is key to understanding everything else. There are places in the universe where the familiar rules of space and time begin to unravel. These are not distant in the sense of being unreachable by thought, but distant in how far they stretch our understanding. Among the most extreme of these regions are black holes, objects so dense and so powerful that they transform the very structure of space-time around them. They are not simply massive stars or exotic remnants. They are gateways into a regime where reality behaves in ways that challenge every assumption we carry. A black hole forms when a massive star reaches the end of its life, after burning through its nuclear fuel. The outward pressure that once balanced gravity disappears. The star collapses under its own weight, compressing matter to extraordinary densities. If the mass is great enough, nothing can stop this collapse. The core continues to shrink, pulling everything inward until it creates a region where the curvature of space-time becomes extreme. At the heart of this region lies what is known as a singularity, a point where density becomes infinite and the known laws of physics break down. Around it forms a boundary called the event horizon. This boundary is not a physical surface, but a limit in space-time. Once something crosses it, there is no path that leads back out. Not even light can escape, which is why these objects appear completely dark. The event horizon marks a profound shift in how space and time behave. Outside this boundary, space and time still function in ways that can be described and predicted. Inside it, the roles of space and time begin to blur. The direction we normally think of as forward in time becomes intertwined with the direction inward toward the singularity. Moving toward the center becomes as inevitable as moving forward in time. Just as we cannot stop time from passing, anything inside the event horizon cannot avoid being drawn deeper. From the outside, a black hole presents a strange picture. If an object falls toward it, an observer, watching from a distance, will see the object slow down as it approaches the event horizon. Its clock appears to tick more and more slowly, its light becoming dimmer and redder. It never seems to cross the boundary. Instead, it fades and freezes at the edge. This is due to the extreme gravitational time dilation caused by the intense curvature of space-time. But from the perspective of the falling object, the experience is entirely different. Time continues normally. There is no sudden stop at the horizon. The object passes through without noticing a sharp boundary at that exact moment, assuming the black hole is large enough that tidal forces at the horizon are not yet extreme. This difference in perspectives highlights the deeply relative nature of time and observation. As the object continues inward, conditions become more severe. The gravitational pull varies dramatically across small distances, leading to what is known as tidal forces. These forces stretch objects along the direction toward the singularity and compress them in perpendicular directions. For smaller black holes, this effect becomes intense even before reaching the horizon, pulling objects apart in a process sometimes described as spaghettification. For larger black holes, this stretching may only become extreme closer to the center. The existence of black holes raises questions about information and the nature of reality. When something falls into a black hole, what happens to the information it carries? In classical physics, information is preserved. The state of a system at one time determines its state at another. But if information disappears into a black hole and is lost forever, this principle would be violated. This leads to one of the most famous puzzles in modern physics, often referred to as the information paradox. On one hand, the laws of quantum mechanics suggest that information cannot be destroyed. On the other hand, the classical description of black holes implies that anything entering them is lost beyond the event horizon. Resolving this tension requires new ideas about how space-time and quantum processes interact. One possible clue comes from the realization that black holes are not entirely black. Quantum effects near the event horizon can lead to the emission of radiation. This process, often called Hawking radiation, arises from the behavior of quantum fields in curved space-time. Pairs of particles can form near the horizon, with one falling in and the other escaping. To an outside observer, the black hole appears to emit radiation. Over extremely long timescales, this radiation causes black holes to lose mass and eventually evaporate. This introduces another layer to the information paradox. If a black hole can disappear completely, what happens to the information it once contained? Does it escape with the radiation, remain encoded in some subtle way, or is it fundamentally lost? These questions remain at the forefront of theoretical research. Black holes are not isolated curiosities. They play a crucial role in the structure and evolution of the universe. At the centers of most galaxies, including our own, lie supermassive black holes with masses millions or billions of times that of the Sunday. These objects influence the motion of stars and gas over vast distances. They can power some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei. When matter falls toward a black hole, it does not simply disappear quietly. It often forms an accretion disk, a rotating structure of hot gas spiraling inward. Friction and gravitational effects heat this material to extreme temperatures, causing it to emit intense radiation. In some cases, powerful jets of particles are launched from the regions near the black hole, extending far into space. These jets can affect entire galaxies, regulating star formation and shaping cosmic environments. Collisions between black holes produce some of the most dramatic events in the universe. When two black holes orbit each other and eventually merge, they release enormous amounts of energy in the form of gravitational waves. These ripples in space-time carry information about the masses, spins, and dynamics of the merging objects. Detecting these waves allows us to observe events that would otherwise be invisible. Black holes also provide a testing ground for our theories of space-time. Their extreme conditions push the limits of general relativity, revealing where it succeeds and where it may need to be extended. They highlight the need for a theory that can unify gravity with quantum mechanics, one that can describe what happens at the singularity and resolve the paradoxes that arise. Some theoretical ideas suggest that black holes may not end in true singularities. Instead, quantum effects could prevent infinite density, replacing the singularity with a more complex structure. Other proposals explore the possibility that black holes could be connected to other regions of space-time, forming bridges or tunnels. These ideas remain speculative, but they show how black holes inspire new ways of thinking about the universe. The study of black holes also changes how we think about time. Near these objects, time behaves in extreme ways. From a distant perspective, processes near the horizon appear to slow down dramatically. From a local perspective, time continues as usual. This duality forces us to accept that time is not absolute, but depends on the observer's position and motion. In a broader sense, black holes represent the limits of our current understanding. They are places where the known laws of physics reach their boundaries and where new principles are likely to emerge. They challenge us to rethink the nature of space, time, and information, pushing us toward deeper insights. As we continue to observe and study these objects, we gain more than just knowledge about a specific phenomenon. We gain clues about the fundamental structure of reality. Black holes are not just endpoints of stellar evolution. They are windows into the deepest workings of the universe, revealing how space-time behaves under the most extreme conditions. They remind us that the universe is not simple or static. It is dynamic, complex, and often counterintuitive. The closer we look, the more we find that our everyday experiences are only a small part of a much larger and more intricate picture. And within that picture, black holes stand as both mysteries and guides, pointing the way toward a deeper understanding of time and space. As we move deeper into the nature of reality, the smooth and continuous picture of space-time begins to break apart. The large-scale universe, governed by the curvature of space-time, appears ordered and predictable. Planets follow orbits, light bends in measurable ways, and the expansion of the universe unfolds according to well-understood principles. But when we turn our attention to the smallest scales, a completely different world emerges. Here, certainty fades, and the universe becomes governed by probabilities, fluctuations, and strange connections that defy classical logic. This is the realm of quantum mechanics, a framework that describes how nature behaves at the scale of atoms and subatomic particles. Unlike the predictable paths of planets, particles in the quantum world do not follow single, well-defined trajectories. Instead, they exist in a range of possible states simultaneously, described by a mathematical object known as a wave function. This wave function encodes probabilities, not certainties. It tells us where a particle might be found, not exactly where it is. One of the most surprising features of this framework is superposition. A particle can exist in multiple states at once until it is measured. It can be in different positions, have different energies, or even move in different directions simultaneously. Only when an observation is made does the particle appear to settle into a specific state. This process, often called collapse, raises deep questions about the role of measurement and the nature of reality itself. In our everyday experience, objects are always in definite states. A ball is either here or there, moving or still. But at the quantum level, this clarity disappears. The world becomes a blend of possibilities, only resolving into definite outcomes when interactions occur. This challenges our intuitive understanding and forces us to reconsider what it means for something to exist. Another remarkable phenomenon in the quantum world is entanglement. When two particles interact, they can become linked in such a way that their properties are no longer independent. Measuring one particle instantly determines the state of the other, no matter how far apart they are. This connection does not depend on distance and seems to occur without any delay. It suggests that at a fundamental level, the universe is deeply interconnected in ways that are not limited by space. Entanglement does not allow for faster-than-light communication, but it does reveal that the structure of reality is not simply built from isolated pieces. Instead, it may be composed of relationships that extend across space. This challenges the classical idea of locality, where objects are only influenced by their immediate surroundings. In the quantum world, separation in space does not always mean independence. The uncertainty principle adds another layer of complexity. It states that certain pairs of properties, such as position and momentum, cannot both be known with complete precision at the same time. The more accurately we know one, the less accurately we can know the other. This is not a limitation of measurement tools, but a fundamental feature of nature. It means that, at its core, reality is not fully determined. There are limits to what can be known. This inherent uncertainty shapes the behavior of particles and systems. It leads to phenomena such as quantum tunneling, where particles can pass through barriers that would be impossible to cross in classical physics. Instead of needing enough energy to overcome a barrier, a particle has a probability of appearing on the other side. This effect is essential in many processes, including those that power stars and enable modern technologies. When we try to combine the principles of quantum mechanics with the concept of space-time, we encounter profound challenges. In the classical picture, space-time is smooth and continuous, but quantum theory suggests that at very small scales, this smoothness may break down. The fabric of space-time could become turbulent, fluctuating with constant activity. This idea is sometimes described as quantum foam, a state where the geometry of space is no longer fixed but constantly changing. In such a picture, distances and durations lose their usual meaning. The concept of a precise point in space or a precise moment in time may no longer apply. Instead, reality becomes a network of interactions and probabilities, where the structure of space-time emerges from deeper processes. Some theories suggest that space itself is built from discrete units, much like matter is made of atoms. These units could be incredibly small, far beyond the reach of current experiments. If this is true, then the continuity we observe is an approximation, a large-scale effect arising from countless tiny components. Other approaches propose that space and time are not fundamental at all. They may emerge from patterns of entanglement and information. In this view, the geometry of space-time is a reflection of how quantum systems are connected. The distances we perceive could correspond to the strength of these connections. Closer regions are more strongly entangled, while distant regions are less so. This perspective suggests a radical shift in how we understand reality. Instead of starting with space and placing objects within it, we start with relationships and interactions. Space emerges from these relationships, not the other way around. Time, too, could arise from the evolution of these connections rather than existing as an independent flow. The role of the observer becomes particularly intriguing in this context. In quantum mechanics, measurement plays a key role in determining outcomes. But what counts as a measurement? Is it the act of a conscious observer, or simply any interaction with the environment? Different interpretations offer different answers, and the debate remains unresolved. Some interpretations suggest that all possible outcomes of a quantum event actually occur, each in its own branch of reality. In this view, the universe constantly splits into multiple versions, each representing a different possibility. While this idea may seem extreme, it arises naturally from the mathematical structure of quantum theory. It implies that reality is far more vast and complex than our single experience suggests. Others propose that there are hidden variables or deeper mechanisms that determine outcomes, even if we cannot observe them directly. These approaches aim to restore a sense of determinism, but they must account for the experimental evidence that supports the probabilistic nature of quantum mechanics. As we explore these ideas, we find that the quantum world does not fit easily into our classical understanding. It requires new concepts, new language, and new ways of thinking. It reveals that the universe is not just a collection of objects moving through space and time, but a web of possibilities and connections. The interplay between quantum mechanics and gravity remains one of the greatest challenges in physics. General relativity describes how space-time curves and evolves, while quantum mechanics describes how particles behave at small scales. Both are incredibly successful in their domains, but they are not yet fully compatible. Combining them into a single, coherent framework is one of the central goals of modern science. Attempts to achieve this have led to the development of various theories, each offering a different perspective on the underlying nature of reality. Some focus on quantizing space-time itself, while others seek to describe all particles and forces as different aspects of a single fundamental entity. These efforts are ongoing, and while no definitive answer has been found, they continue to push the boundaries of knowledge. What becomes clear through all of this is that reality is far more subtle than it appears. The solid world we experience emerges from a foundation that is fluid, uncertain, and deeply interconnected. Space and time, once thought to be the stage on which events unfold, may themselves be products of deeper processes. This realization does not make the universe less real. Instead, it makes it richer and more complex. It invites us to look beyond appearances and to explore the hidden layers that give rise to everything we observe. As we continue to investigate the quantum nature of the universe, we move closer to understanding the true foundation of space and time. Each discovery reveals new questions, new mysteries, and new possibilities. And in this strange and fascinating realm, where certainty gives way to probability and separation gives way to connection, we begin to glimpse the deeper structure of reality itself. The universe is not standing still. It is not a fixed structure frozen in time. On the largest scales, everything is in motion, not because galaxies are simply flying through space, but because space itself is expanding. This idea changes how we understand distance, motion, and even the future of the cosmos. It reveals that the fabric of space-time is dynamic, stretching over time and carrying galaxies along with it. When we look at distant galaxies, we find that their light is shifted toward the red end of the spectrum. This phenomenon, known as redshift, is a key piece of evidence for cosmic expansion. It shows that these galaxies are moving away from us. But the deeper interpretation is even more profound. They are not just moving through space. The space between us and them is growing. The wavelength of the light stretches along with space, making it appear redder. This pattern is not random. The farther away a galaxy is, the faster it appears to recede. This relationship reveals a universe that is expanding uniformly in all directions. From any point of view, it appears that everything else is moving away. This does not mean we are at the center. Every observer, no matter where they are, would see the same pattern. The expansion is built into the structure of space itself. To visualize this, imagine again the surface of an inflating balloon. As the surface expands, every point moves away from every other point. There is no special center on the surface. The expansion is a property of the surface itself. In a similar way, our universe expands in all directions, not into something else, but as its own geometry evolves. This expansion has a history. It began in the early universe and has continued for billions of years. At first, it was extremely rapid. Then it slowed down as gravity worked to pull matter together. Galaxies formed, clusters emerged, and large-scale structures developed. For a long time, it was expected that gravity might eventually slow the expansion enough to stop it or even reverse it. But observations revealed something unexpected. Instead of slowing down, the expansion of the universe is accelerating. Distant galaxies are moving away faster and faster over time. This discovery was surprising because it suggested that something is counteracting gravity on cosmic scales. Instead of pulling everything back together, the universe is being pushed apart more strongly as time goes on. The cause of this acceleration is not fully understood. It is attributed to a mysterious component called dark energy. This form of energy appears to be associated with space itself. As space expands, more of this energy seems to come into existence, driving further expansion. Unlike matter and radiation, which dilute as the universe grows, dark energy maintains or even increases its influence. Dark energy dominates the large-scale behavior of the universe. It shapes the future, determining how the cosmos will evolve over immense timescales. If the acceleration continues, distant galaxies will move farther and farther away, eventually becoming unreachable. The observable universe will shrink in terms of what can be seen and interacted with, even as the total universe continues to expand. The expansion of space also affects how we think about motion. In everyday life, we think of motion as objects moving through a fixed background, but on cosmic scales, the background itself is changing. Galaxies are not simply traveling through space like ships through water. They are embedded in space, and as it expands, the distances between them grow. This distinction becomes important when considering the limits of motion. There is a speed limit in the universe, the speed of light, which applies to objects moving through space. But the expansion of space itself is not limited in the same way. Over very large distances, the rate at which space expands can exceed the speed of light. This does not violate the laws of physics because it is not motion through space, but the growth of space itself. As a result, there are regions of the universe that are moving away from us so quickly that their light will never reach us. These regions lie beyond what is called the cosmic horizon. It marks the boundary of the observable universe, the limit of what we can ever see. Beyond it, the universe continues, but it is forever hidden from view. The expansion of the universe also has implications for the past. When we look at distant objects, we are seeing them as they were long ago. Light takes time to travel, so observing distant galaxies is like looking back in time. The farther away something is, the older the light we receive from it. This allows us to study the history of the universe, tracing its evolution from its early stages to the present. The cosmic microwave background provides a snapshot of the universe when it was very young, just a few 100,000 years old. By studying its properties, we can learn about the conditions at that time and how they led to the structures we see today. The expansion of space has stretched this ancient light, cooling it and spreading it across the sky. As we look deeper into space, we see galaxies at different stages of development. Some are young and forming stars rapidly. Others are more mature, with well-defined structures. This diversity reflects the ongoing evolution of the universe, shaped by the interplay of expansion, gravity, and the properties of matter and energy. The future of the universe depends on the balance between these factors. If dark energy continues to dominate, the expansion will accelerate indefinitely. Galaxies will drift apart, stars will burn out, and the universe will become colder and darker over time. This scenario is sometimes referred to as heat death, where the energy available for doing work becomes evenly distributed and no large-scale processes can occur. In more extreme possibilities, the acceleration could become so strong that it tears apart structures at every level. Galaxies, stars, planets, and even atoms could be pulled apart by the expansion. This hypothetical scenario, sometimes called the Big Rip, represents one possible outcome if the properties of dark energy change over time. Alternatively, if dark energy behaves differently than currently understood, the expansion could slow or reverse in the distant future. The universe might collapse back on itself in a big crunch or transition into a new phase. These possibilities remain speculative, but they highlight the uncertainty in our understanding of cosmic evolution. The expansion of space also raises deeper questions about the nature of the universe as a whole. Is it infinite or finite? Does it have a boundary, or does it curve back on itself in higher dimensions? Observations suggest that the universe is very close to flat on large scales, meaning that its geometry does not have strong curvature. But this does not necessarily determine its overall size or shape. The concept of expansion is closely tied to the geometry of space-time. The equations that describe this geometry allow for different types of universes, depending on the amount of matter, energy, and curvature present. By measuring these quantities, we can determine which model best describes our universe. Current observations indicate a universe composed mostly of dark energy, with smaller contributions from dark matter and ordinary matter. This composition influences how expansion evolves over time. It shapes the formation of structures and the overall dynamics of the cosmos. As we refine our measurements, we continue to uncover new details about expansion. Subtle differences in observed values lead to ongoing debates and investigations. These discrepancies may point to new physics or deeper layers of understanding. The expansion of the universe is not just a distant phenomenon. It is happening everywhere, even here. On small scales, gravity and other forces hold structures together, preventing them from expanding. Atoms, planets, and galaxies remain bound. But on larger scales, where these forces are weaker, expansion dominates. This dual behavior highlights the complexity of the universe. Different processes operate at different scales, creating a rich and varied structure. Understanding how these processes interact is key to understanding the cosmos as a whole. As we reflect on the expansion of space, we see that it is not just a feature of the universe, it is a fundamental aspect of its nature. It shapes how distances evolve, how light travels, and how structures form and change over time. The universe is not static, it is a living system, constantly evolving, constantly expanding, constantly revealing new aspects of itself. And as we continue to explore, we deepen our understanding of the forces that shape it, bringing us closer to uncovering the true nature of time and space. There is something in the universe that we cannot see, cannot touch, and cannot directly measure in the way we measure ordinary matter. Yet it shapes the fate of everything. It does not form stars, it does not emit light, and it does not cluster in the familiar ways we associate with galaxies and gas. And yet, it dominates the cosmos. This mysterious component is what we call dark energy, and it may be the most profound clue we have about the true nature of space and time. The discovery of dark energy did not come from a single experiment, but from a pattern that emerged as scientists studied distant galaxies. When astronomers measured how fast these galaxies were moving away, they expected to see the expansion of the universe slowing down over time due to gravity. Instead, they found the opposite. The expansion was accelerating. Galaxies were not just drifting apart, they were speeding up as the universe aged. This observation forced a radical shift in understanding. Something was pushing the universe apart, overcoming the attractive pull of gravity on the largest scales. This force did not behave like anything previously known. It did not diminish with distance in the way gravity does. Instead, it seemed to grow more influential as space itself expanded. To understand dark energy, we must first reconsider the nature of empty space. In classical thinking, empty space is truly empty, containing nothing at all. But quantum theory tells a different story. Even in a perfect vacuum, there are fluctuations, tiny bursts of activity where particles appear and disappear. This suggests that space has an intrinsic energy, often called vacuum energy. One possibility is that dark energy is simply this vacuum energy on a cosmic scale. If space itself has energy, then as the universe expands and creates more space, the total amount of this energy increases. This could drive the accelerated expansion we observe. However, when scientists try to calculate the expected value of vacuum energy from quantum theory, the result is vastly larger than what we observe. This mismatch is one of the greatest unsolved problems in physics. Another way to think about dark energy is as a property of space-time itself. In the equations that describe the geometry of the universe, there is a term that can represent a constant energy density filling space. This term can act as a kind of repulsive gravity, pushing space outward rather than pulling it inward. When this term is included, it can account for the observed acceleration. This idea suggests that dark energy is not something added to space, but something inherent in its structure. It is part of the fabric of the universe, influencing how it evolves over time. Unlike matter and radiation, which become less dense as the universe expands, dark energy remains constant or nearly constant in density. As a result, its relative importance grows over time, eventually dominating the dynamics of the cosmos. The presence of dark energy has profound implications for the future of the universe. If it continues to drive acceleration, then distant galaxies will move farther and farther away. Over immense timescales, they will recede beyond the cosmic horizon, becoming invisible and unreachable. The night sky, once filled with countless galaxies, would grow increasingly dark as more and more of the universe slips beyond our view. In such a future, observers in distant epochs might see only their own galaxy and a few nearby companions. The evidence for the Big Bang and the expansion of the universe could become inaccessible, hidden behind the relentless growth of space. This raises a striking thought. Our current view of the cosmos, rich with information about its history and structure, may be a temporary window, available only during a particular era. Dark energy also raises questions about the ultimate fate of all structures. In the standard picture, galaxies, stars, and planets remain bound by gravity and other forces, even as the universe expands. But if the properties of dark energy were to change, the outcome could be far more dramatic. In some theoretical scenarios, the repulsive effect of dark energy could grow stronger over time, eventually overcoming all forms of binding. In this extreme case, the expansion would not only separate galaxies, but also tear apart stars, planets, and even atoms. The fabric of space-time itself would be stretched to such an extent that no structure could remain intact. This hypothetical scenario, often called the Big Rip, represents one possible fate of the universe if dark energy behaves in certain ways. However, current observations suggest that dark energy behaves more like a constant, leading to a more gradual and less violent future. The universe would continue to expand and cool, with energy becoming more evenly distributed. Stars would exhaust their fuel, galaxies would grow dim, and the cosmos would approach a state of maximum entropy. This scenario is often referred to as heat death, where no large-scale processes remain to create new structures or maintain existing ones. Despite these insights, the true nature of dark energy remains unknown. It could be a property of space itself, a field that permeates the universe, or a sign that our understanding of gravity is incomplete. Some theories propose that the laws governing space-time may need to be modified on large scales, altering how gravity behaves over vast distances. These alternative models attempt to explain the observed acceleration without invoking a separate form of energy. Instead, they suggest that gravity becomes repulsive under certain conditions, or that the geometry of the universe evolves in unexpected ways. While these ideas are intriguing, they must match the wealth of observational data that supports the presence of dark energy. The study of dark energy is closely tied to precise measurements of the universe. By observing distant supernovae, mapping the distribution of galaxies, and studying the cosmic microwave background, scientists gather clues about how expansion has changed over time. Each measurement helps refine our understanding, narrowing down the possibilities and guiding theoretical developments. One of the key challenges is that dark energy does not interact with matter in ways we can easily detect. It does not clump or form structures. Its presence is inferred through its effects on the expansion of space. This makes it difficult to study directly, requiring careful analysis of subtle signals spread across vast distances. As technology advances, new observations may provide deeper insights. More powerful telescopes and surveys will map the universe in greater detail, revealing patterns that could distinguish between different models of dark energy. These observations may uncover variations over time or space, offering clues about its origin and behavior. The mystery of dark energy also connects to deeper questions about the nature of reality. If space itself has energy, what does that mean for the structure of the universe? Why does this energy have the value we observe, and not something vastly larger or smaller? These questions touch on fundamental principles and may require new theories that go beyond current frameworks. Some ideas suggest that the value of dark energy could be related to the existence of observers. In a universe where this value were much larger, galaxies and stars might never form, making the emergence of complex structures unlikely. In this view, the observed value is not random, but constrained by the conditions necessary for life and observation. While this perspective is controversial, it highlights the deep connections between cosmology and fundamental physics. The presence of dark energy also influences how we think about the origin of the universe. It may play a role in the early stages of expansion, connecting to the period of inflation that occurred shortly after the Big Bang. Both involve accelerated expansion, though at vastly different scales and times. Understanding one may provide insights into the other. As we continue to explore, it becomes clear that dark energy is not just a detail of cosmology. It is a central feature of the universe, shaping its past, present, and future. It challenges our understanding of space, time, and energy, pushing us to develop new ideas and new theories. The universe, once thought to be governed by familiar forces and simple principles, reveals itself to be far more complex. Dark energy stands as a reminder that even in the vast emptiness of space, there are forces at work that we do not yet fully comprehend. And as we look deeper into the cosmos, we are not just observing distant galaxies. We are uncovering the hidden properties of reality itself, moving closer to understanding the true nature of the universe and the role that time and space play within it. At the edge of everything we know, where space stretches into the unknown and time seems to dissolve into abstraction, there is a growing realization that our current understanding may only be a surface layer of a much deeper reality. Every idea we have explored so far, from the curvature of space-time to the expansion of the universe, from quantum uncertainty to dark energy, points toward a consistent theme. The universe is not built from simple, fixed ingredients. It is dynamic, relational, and possibly emergent from something even more fundamental. The question that naturally arises is whether space and time themselves are truly fundamental, or whether they are approximations of a deeper structure. For centuries, physics treated space as a container and time as a universal flow. Even when relativity showed that they are intertwined, they were still assumed to be part of the basic framework of reality. But modern developments suggest a different possibility. Space and time may not be the foundation. They may be the outcome. To understand this idea, we must consider how deeply space and time are tied to our perception. Every experience we have is structured in terms of where and when objects are located in space. Events occur in time. Our minds organize reality through these coordinates. It is difficult to imagine existence without them, but difficulty does not mean impossibility. It may simply reflect the limits of human intuition shaped by everyday scales. At the smallest scales, where quantum mechanics dominates, the notion of a smooth, continuous space begins to lose clarity. Particles do not behave like tiny objects moving through fixed paths. Instead, they exist as probabilities spread across regions. Interactions are not localized in the classical sense. They are described by mathematical relationships that do not require a predefined background space. This has led some physicists to propose that space itself may emerge from these relationships. Instead of starting with space and placing particles within it, we begin with interactions and allow space to arise as a way of organizing them. In this view, distance is not fundamental. It is a measure of how strongly systems are connected. What we perceive as geometry could be a reflection of underlying patterns of correlation. Time may emerge in a similar way. Rather than being a universal parameter flowing independently, time could arise from the ordering of changes in these relationships. What we call the passage of time might be the progression of states within a deeper structure that does not itself contain time in the familiar sense. One of the most intriguing ideas supporting this perspective comes from quantum entanglement. When particles become entangled, their properties become linked in ways that do not depend on spatial separation. The strength of their connection does not diminish with distance. This suggests that entanglement might be more fundamental than space itself. Perhaps space is a way of representing patterns of entanglement in a simplified form. If this is true, then the fabric of space-time could be like a map drawn from deeper connections. Just as a network of relationships can be represented as a geometric structure, the universe we observe might be a large-scale projection of a more abstract underlying reality. In this picture, geometry is not the starting point, but the result. This idea becomes even more compelling when we consider attempts to unify quantum mechanics and gravity. Both theories are extremely successful in their domains, but they describe reality in very different languages. Quantum mechanics deals with probabilities and discrete interactions, while general relativity describes smooth curvature of space-time. Bridging this gap has been one of the central challenges of modern physics. Some approaches suggest that space-time itself should be quantized, composed of discrete building blocks. At this level, geometry would not be continuous, but made of fundamental units connected in specific ways. These connections would determine distances, curvatures, and even causal relationships. The smooth space we experience would then emerge from averaging over vast numbers of these tiny structures. Other approaches go further and suggest that even these building blocks are not spatial in nature. Instead, they are abstract entities defined by mathematical relations. Space and time emerge only when these relations are interpreted in a macroscopic context. In this sense, the universe is not made of things in space, but of relationships that give rise to space. This shift in perspective has profound implications. It suggests that the universe is fundamentally informational, not in the sense of human communication, but in the sense that its most basic description is about patterns, correlations, and transformations. Physical reality could be understood as a vast network of information processing, where space and time are emergent features of this process. If space and time are emergent, then the question of what lies beyond them becomes meaningful. We are not asking what exists outside space in a spatial sense, but what underlying structure gives rise to space itself. Similarly, we are not asking what happens before time, but what generates the ordering that we perceive as time. In this deeper framework, familiar concepts like distance, duration, and even causality may not exist in their usual form. Instead, they may arise from more primitive relationships that do not distinguish between space-like and time-like separation. The distinction between past and future could be a large-scale feature emerging from microscopic rules that do not explicitly contain time. This perspective also changes how we think about the origin of the universe. The Big Bang, traditionally viewed as the beginning of space and time, may instead represent a transition in this deeper structure. Rather than the creation of everything from nothing, it could be the emergence of space-time from a pre-geometric state. In this view, the universe did not begin in time. Time itself began with the universe. If this is the case, then asking what happened before the Big Bang may be similar to asking what is north of the North Pole. The question assumes a framework that may not apply at the most fundamental level. Instead, we may need entirely new concepts to describe the underlying reality. There are also implications for the nature of change. If time emerges from more basic processes, then change itself is not fundamental, but derived. The evolution of the universe would be described not as motion through time, but as a sequence of transformations within a timeless structure. Our perception of flow would be a consequence of how we experience these transformations. This idea resonates with certain interpretations of quantum mechanics, where the notion of a single, evolving history is replaced by a collection of possible outcomes. In such interpretations, the universe does not follow one fixed path, but contains a spectrum of possibilities. The appearance of a single timeline may arise from the way observers interact with this underlying structure. Even gravity, which we have understood as the curvature of space-time, may need to be reinterpreted. If space-time is emergent, then curvature itself must be a derived concept. Gravity could instead reflect how underlying relationships change in response to energy and information. What we perceive as attraction might be the manifestation of deeper constraints within a relational system. This line of thinking suggests that all fundamental forces may be different expressions of the same underlying structure. Electromagnetism, nuclear forces, and gravity could all arise from patterns of interaction within a unified framework. The distinctions we observe might reflect different ways these patterns organize at large scales. Despite its abstract nature, this approach is not purely speculative. It is motivated by attempts to resolve inconsistencies between our best theories and to explain phenomena that remain poorly understood, such as dark energy, black hole information, and the nature of quantum measurement. Each of these puzzles may be pointing toward a deeper level of description. As we move toward this deeper understanding, we are also forced to reconsider the role of observation. In a universe where space and time are emergent, the act of observation may play a more fundamental role than previously thought. Observers are not separate from reality, but part of the network of relationships that defines it. What we call measurement could be an interaction that helps define structure itself. This raises profound questions about objectivity. If space and time emerge from relationships that include observers, then the distinction between observer and observed becomes less clear. Reality may not exist independently in the way classical physics assumes. Instead, it may be co-defined by the interactions that constitute it. Even with these ideas, we must remain grounded in empirical evidence. Any theory of deeper reality must reproduce the successful predictions of existing physics. It must explain why space-time appears continuous at large scales, why gravity behaves as it does, and why quantum mechanics produces the results we observe. The challenge is not only to imagine new frameworks, but to connect them to measurable phenomena. As research continues, new mathematical structures and experimental techniques may provide clues. High-energy physics, cosmology, and quantum information theory are all converging toward questions about the nature of space, time, and reality itself. Each offers a different window into the same underlying mystery. What becomes increasingly clear is that the universe is not a simple machine built from basic parts. It is a deeply interconnected system where structure, dynamics, and observation are intertwined. Space and time, once thought to be the foundation, may instead be expressions of something more abstract and fundamental. At this stage of understanding, certainty gives way to exploration. We are no longer describing a finished picture of the universe, but uncovering layers of structure that may continue far beyond our current reach. Each answer reveals new questions. Each discovery points toward deeper levels of reality. And so, at the edge of space and time, we find not an end, but an invitation. An invitation to continue exploring, to question assumptions, and to seek the deeper principles that give rise to everything we see, everything we experience, and everything we are.